In this video, we're continuing section 6.3 on the unit circle, and we're going to talk about something called the Pythagorean identity. Okay, and then we'll do an example after that. Okay, so I want to take a look at this picture here that I have of a unit circle. So in this picture, let's suppose that this angle right here, I'm going to call it theta. So the angle theta corresponds to this point whose coordinates are x and y. And it's a unit circle, so my radius is 1. My hypotenuse of this right triangle is 1. Okay, so in this right triangle, this horizontal length is x. That horizontal length is x, and that vertical length is my y coordinate. Okay, and well, what I'm going to do is, let's say what y and x are using our trig functions. I know that the y coordinate is sine of theta, and then I know that that x coordinate is cosine of theta. All right, those are just the definitions of sine and cosine. And now, because this is a right triangle, let's go ahead and use our Pythagorean theorem. So by the Pythagorean theorem, I'm just going to abbreviate THM theorem, that tells me that when I do x squared plus y squared, that equals the hypotenuse squared, which is 1 squared. 1 squared. Okay, and if I plug in for what x is cosine, and what y is sine, well, x squared gives me cosine of theta getting squared. But remember, the way I write an exponent on a trig function is I put it here. That just means cosine getting squared. Similarly, when I plug in for y, I'll get sine squared theta, and then 1 squared equals 1. Okay, and we just derived a really important trig identity, that cosine squared plus sine squared equals 1. This is perhaps the single most trig identity that we'll have. So cosine squared plus sine squared equals 1. This is actually where it comes from. It comes from doing Pythagorean theorem on the unit circle. One quick thing I want to mention about this is, in my picture, I kind of assumed that this angle corresponded to a point in the first quadrant. But it turns out that this works even outside of that first quadrant. So even if I was over here, or over here, or over here, it works in any of those, since when I plug in for x or y in any of those quadrants, they're going to get squared. And when I square them, it turns everything non-negative. So it gets rid of the problem where some of my coordinates could be negative. And then it'll end up working. Okay. All right, so let's take a look at an example. Let's take a look at an example problem now. All right, so this problem says that if theta is in between pi over 2 and pi, okay, and if sine of theta is 2 over 3, I want to evaluate in part A cotangent of theta, and in part B secant of theta. Okay, so the problem tells me that theta is between pi over 2 and pi. So in my unit circle, so if I draw my axes, and then I draw a circle, so if I draw a circle, well, I know pi over 2 is up here, that's at the 90-degree mark. Pi is over here, that's at 180 degrees. So theta is somewhere between those two. So that is my second quadrant. So theta is in quadrant 2. Okay. Unfortunately, there's no spot on the unit circle. There's no nice spot on the unit circle where sine is 2 over 3. Like if I think back to my unit circle a couple pages ago, I know sine is my y value. Sine is my y value on the unit circle. But if I look at all the points on the unit circle, any of these points that I have here, all these nice points, well, none of these y values anywhere here are equal to 2 over 3. Okay, so then, well, how do I do this? How do I do a problem like this then, if it's not even one of these nice spots on my unit circle that I have? Okay, so let's scroll it back down to our problem. So what I'm going to say is I don't know what this angle is. At least it's not one of the nice angles that I have on my unit circle. So how can I do this? I'm going to draw some point in this quadrant. It doesn't really matter where. And now let me connect that with the origin. Okay, and whatever this angle theta is, I'm just going to label that. So theta is a mystery angle. I'm going to label that. Okay. And if I drop a perpendicular line here to make a right triangle, all right, and I call this vertical length y, and I call that horizontal length x, I'm going to now call this hypotenuse, let me just call it r. Typically in a unit circle, we'd let r be equal to 1, but for the time being, let me just call it r. Let me not assign a value to it. Because what I'm going to do now is, since the problem tells me that sine is equal to 2 over 3, if I think back to what sine was equal to when we just used SOHCAHTOA, well, sine was equal to y over r. So sine of theta was equal to y over r, right? In my unit circle, if I drew just like a right triangle, and I call this theta, and this is y, and this is x, and this is r. If I use SOHCAHTOA, sine of theta is the opposite over the hypotenuse, but the opposite side to theta is y, and the hypotenuse is r. So sine of theta in general was equal to y over r, but usually in a unit circle, our radius is 1, and that's why this fraction just becomes y. Okay, but I'm going to keep it more general for the time being. Let's just keep the radius as r. Okay, so now I really want so I need sine of theta to equal 2 over 3, which means I need y over r to be equal to 2 over 3. So how can we accomplish that? Because there's many things that y and r could be so that the fraction becomes 2 over 3. But maybe the simplest is if we just let y be equal to 2 and to let r be equal to 3. So let me label that in the picture here. I'm going to let my y value be equal to 2, and I'm going to let r, let me zoom it in here. I'm going to let r be equal to 3. Okay, so like in part A, I am trying to figure out what cotangent of theta is. So cotangent of theta. Okay, and I know cotangent of theta in my unit circle is x over y. Okay, so I know what y is. I know my denominator. My denominator is 2, but I don't know x yet. So, well, we have a right triangle, so let's use some Pythagorean theorem. So if I do my Pythagorean theorem, we get x squared plus y squared equals 3 squared. Okay, so this is where we're seeing a similar idea to what we saw up here when we derived this identity. We're doing some Pythagorean theorem. And now if I plug in, we get, whoops, sorry, I didn't even plug in for y. Let me plug in for y. I know y is 2. So y is 2. So I get x squared, and then this is 9. I'm going to subtract the 4 over. So x squared equals 5. And then square rooting, I get x equals plus or minus root 5. So which is it? Is x positive root 5 or negative root 5? Well, my point is in the second quadrant. So in quadrant 2, my x coordinate is negative, right? If my point is over here, my x value should be negative. Okay, so I'm going to label that. This x coordinate should be equal to negative root 5. X value is negative root 5. Okay, so that's going to be the numerator of my fraction. I'll get negative root 5. And now I got it. I got cotangent of theta. It's negative root 5 over 2. So notice we were able to figure out what it was without even knowing the angle. Just from the given information that sine of theta equaled this fraction, I was able to construct all the sides of the right triangle, and from that was enough information to figure out cotangent of theta. All right, so now let's get part B. Part B asks me for secant of theta. So secant of theta. So I know secant is the reciprocal of cosine. This is 1 over cosine. So, okay. Well, let's go to our general right triangle here. What's cosine equal to? Cosine is equal to the adjacent over hypotenuse if I use my SOHCAHTOA. And the adjacent to theta is x, and the hypotenuse is r. So that gives me x over r. So for secant, well, I got to reciprocal that. So that is going to be r over x. All right, so my radius was 3. My x value was negative root 5. And I got it. I got it. The problem didn't say I have to rationalize the denominator, so it's totally fine to leave that root in the denominator.